Hello everyone, my name is Dr. Michael Okereke. I welcome you to my channel, this Getting Started with Modeling YouTube channel. Today I'm going to make a video on pressure vessels, and especially their design and analysis of their mechanical response. This time around we're going to use MATLAB as a modeling tool to script the behavior of a pressure vessel. The idea is that you can then use this code, this script, as a design tool to investigate the behavior of your pressure vessel. We're going to use MATLAB to do this. It's quite a very basic introduction to using MATLAB as a scripting software for analysis of a really practical structure as pressure vessels. In this video, the pressure vessel that we'll be focusing on is a cylindrical pressure vessel. So if this is the kind of content that you're interested in, please do subscribe to this channel and click on the notification button so that when contents like this are created, you'll be one of the first that would be seeing it. So let's quickly go over to the PowerPoint slide that I've prepared to support this presentation. So this is a design of a typical cylindrical pressure vessel. So this could be a pressure vessel that contains nitrogen gas, or maybe compressed air that sits on the outside of an industrial firm. And at the base here you've got concrete base upon which it is connected, so it sits outside, and the fluid, the pressure inside obviously is higher than the pressure outside. So if we look inside the cylinder, this is kind of the thing you will see. So the red lines here indicate the pressure, and obviously PI is internal pressure. So we can pick out a section within this pressure vessel. If you pick out a point like this in this pressure vessel, so this infinitesimal element, this stress element, would consist of three stresses. So every point in this pressure vessel will be subjected to three stresses, one being the radial stress, another being the axial stress, and the other being the tangential stress. So, and they're acting at the same time during the operation of this. And this is why it's really important to understand what these values are and to be able to use them if you're going to design a pressure vessel. So the cylindrical pressure vessel is what we'll be dealing with in this scripting exercise, and the objective is to create a MATLAB script for analysis of the mechanics of such vessels. Mechanics is really the objective here, to understand the stresses and the strains and the displacement. We're not looking at things around thermodynamics or fluid response. The objective here is really to create a MATLAB script that can explore the mechanics of pressure vessels. Okay, so the domain, what is the domain? So the domain that we'll be dealing with, obviously cylindrical, defined with a given diameter. So this diameter could be 200, it could be 400. In this case, I've used 0.2 meters for my diameter. The thickness of this pressure vessel is 5 millimeters, or 0.005, and the pressure inside is 10 megapascal. The material for the design of this pressure vessel would be typically a steel material of 210 gigapascal Young's modulus and a Poisson ratio of 0.33. So these are the information that we're going to put into the code as we begin to draft this MATLAB script for analysis of the mechanics of a cylindrical thin-walled pressure vessel. So, being a design tool, we want to know what the equations that define the mechanics of this pressure vessel. And here you have the equations. So the tangential pressure vessel is the biggest stress that you normally will see. So it's equal to the pressure inside, P, times the radius divided by T. The axial pressure vessel is half of that, and the radial pressure vessel is basically the negative of the pressure load. The other terms that are important to consider are things like the tangential strain, the strain that you get as this pressure vessel continues to expand under the load of the pressure. So the tangential strain, which is again the biggest strain that you will get in this model, is 1 over the Young's modulus in bracket tangential stress minus Poisson ratio times tangential axial stress. The extension of the radius, so how much is the radial extension growing due to the effect of pressure on the load. So again, the formula is given there. And finally, the maximum shear stress, which is a measure of the distortion that you will see on the pressure vessel, is PR over 2T. So we're going to use these things in our design. Since we want to develop a script, there has to be an algorithm, a flow chart that defines how our script would work. So what I would want to recommend is you divide the creation of your script into 3 sections. A concept about what the input section would be, the computational engine where you implement the equations in the model that we have in the model that we are looking at, and then a display section or an output section where you show the result. So this tends to be the way that I will position or arrange my scripting if I'm going to begin to script. So I have an input section, a computational engine section, and then a display section. So if you have a flow chart like this for your scripting, in this case for the pressure vessel we're working with, then you are in a good place. So now we've got this information. So let's go ahead and now begin to look at how we can script this, and we're going to use MATLAB to do this. So here we are already in an opened MATLAB script. So what we're going to go straight away is to open a new script. So right at the top end here, there is this new script button, or you just press Ctrl N. But we're going to create new script. And so you've got the MATLAB editor that we're going to use to create our code. So I'm going to call this. So the first thing I'll do, obviously, you put a 2% to create a heading. So I'm going to call this script a cylindrical pressure vessel analyzer. Okay, something like that. It's a good thing to give your code a distinctive name, so that it becomes the name that it would use if you're going to convert that into something more meaningful in future. So Cyll pressure vessel, and I'll give actually what that means. So it's basically a thin-walled cylindrical pressure vessels analyzer. So that's what we want. Now these are basically starting up with your code. So who is the author? Myself, Dr. Michael Okereke. And what is the date? Again, it's part of things you need to do if you're going to work on a code like this. So let's use today's date. What version of code? It is the very first version of this code. And what is the code about? So I like to give some information about what the code about. So this is a simple. Okay, so that's the about section of the code. Created. You can tap this bit in a bit if you want, so that you can it looks better and well displayed, so for you to use. So we've got the kind of housekeeping, the top end of the script established. The other thing we can then do, I like to divide my code into 3 sections: the input section, the computational options, computational engine, the computational engine section, and then finally the output stroke display section. So typically this kind of things, output display section, computational engine section, and then input section. So this is obviously so that it can tie up with the original design we have in our PowerPoint slide, which I'll show you now. So this is a PowerPoint slide. So we've got an input section, input parameter section, computing engine or computational options or computational engine section, and then an output section. So actually the names I've used here is input section, computational analysis, and output section to define the 3 sections in the code. So we'll probably use the same even for our design here. So let's go back to MATLAB. So I'm going to change this to computational analysis. Again, analysis. So what do we do right at the top end here? So it's a very basic code. I'll tend to divide this into, again, more sections. So let's start with the geometric information, geometry. So if we zoom in, geometry, and in the geometry details. So within our geometry details, what would we have? So I typically would have, okay, this is something I need to do. So because this is MATLAB, I like to create a variable that I'll store all the information that I'm going to work with. So I'm going to call it the pressure vessel data.d would become diameter. So I'll call this d as a diameter. So let's call this 4 e raised to power minus 3, which is 0.4 meters. And I'll call this, I'll give it a name, I'll call it my diameter. The unit of my diameter is in meter. So things like this, just to show what I'm trying to do. So I've got meter, diameter. Then the next one is my PV data dot r. Okay, so maybe if that's what we want. So obviously we want this to be PV data dot d divided by 2. So this becomes the radius of the cylinder. Again, the unit is in meter. So the other term that is important is PV data dot t. I know I want it to be 5 e raised to power minus 3 because it's 5 millimeter is a thickness. So this is a thickness, and its unit again is in meter. Maybe the next thing I could have here will be the material properties that we want to use. So I could still have PV data dot e equal to, want this to be 210 e raised to power 9, which is Young's modulus. Unit is Pascal. So the other PV data that we would want would be the Poisson ratio, which is lowercase v. So there's 0.33 Poisson ratio. So unit dimensionless. Right, so these are the main terms that we need in our input section of this code. So we've listed out the geometric details and the material details. There's really not much else we can do with this input section. Again, if things start changing and you want to increase the input range, then this is this is what you can do. The first term we would want to have here is PV. Still, I call it data, but this will be my sigma t. So the tangential stress, we know we have a formula for it, and the formula is PV data dot p times PV data dot r for radius in bracket divided by t, which is PV data dot t. Okay, now the next one is PV data dot sigma lowercase sigma a, which we know from our formula is basically half of PV data. So it will be PV data dot t divided by 2. Now PV data dot sigma r, which is the radial stress, is basically equal to the negative of PV data dot. So we've got that. Of course, we've got the maximum stress. So PV data dot tau max. Okay, we could type it out of dot sigma a. So because the both of them are exactly the same. Now the next one is PV. All this result within one variable. Sigma epsilon t. So this basically talks about the tangential strain, and we know the tangential strain is equal to 1 divided by PV data dot e, okay, times bracket PV data dot sigma t minus PV data dot. So dots, so Poisson ratio, which we know is V times PV data dot sigma A. So this is what we had. That's what we have by our formula for PV. Yes, our formula for epsilon t. So we can confirm that again. So what we're trying to type is this 1 over t, 1 over f Young's modulus in bracket sigma t minus v, sigma a, sigma c minus v, sigma a. So after that, then we can then look at the next one, which is this PR squared over 2et bracket 2 minus v. So let's go back to MATLAB. Okay, so we've got that done. So the next bit we need to do would be PV data dot lowercase delta c, which is the radial expansion of the cylinder. So what we have is the pressure first, which is PV data dot p times, I'll put in bracket PV data dot r squared, we know that, okay, times, so the term at the top is 2 minus PV data dot v, where v is the Poisson ratio, bracket, divided, all that product divided by 2et, 2 times PV data dot e, and then finally times PV data dot t. Okay, so if we zoom out, so what we have here, if I go back there, so what we have here basically shows us a little bit. So we've got the pressure times the radius all squared times 2 minus the Poisson ratio divided by 2 times E times T, 2 times E times T. So we've got that information there. Now, so that's all, those are all the computational analysis options files that we need, and then we go into the output section. So how do we display this result? Obviously this result has been already written properly, so the only thing for us to display is just to output that information on the window. So first thing to do is to store the stroke save the data, save. So how do we save it? So it's a simple command. So we're going to use save comma bracket. So what would we do? So we're going to give it a file name. So I'm going to call it maybe Cyllndrical results. Okay, so something like this, cylindrical pressure vessel analyzer results. And obviously what you want to save is PV data only, because so everything you've done has been basically saved in that point. And then maybe on the command window, so you could say, okay, I want to display results on command window. I mean, this is just for the purpose of outputting into the MATLAB command window. So what are we going to do? So I'm going to use the display function. So display, and then this will be the set of parameters from analysis of Cyll pressure vessel data, pressure vessel analyzer. So let's say this is what we want, and then we can, so once we put that, then we can go back and put, okay, display PV data. So it will output this information. We're not going to suppress it, we're going to leave it so that the window can get. Then the final thing I like to do, just take a bit of ownership to the code because it belongs to you. So I'll put a line at the base of the code, and then basically put here again that the copyright information C. So the copyright 2021 Dr. Michael Okereke. So you could put a contact email and then maybe a phone in case someone wants to contact you about this. These are just spurious numbers. Okay, 01234 5676 77 5678 789 10. Okay, so if this is the kind of thing that you're interested in, so you go a bit of information about how they can contact you if someone wants to utilize this code. So this is a simple way of how you can actually create a code. So I'm going to save that. You go to the top of the file, so there's a save button, you click on save. So if you've saved the file, so the file is now saved. If you look at the top end, you can see I've called it the COPV analyzer, and it's saved. I mean, one thing we can then do is just to, so I'll clear the screen, clear the workspace, and then see what happens when you run this code. So if I run the code, okay, so the p-value was not assigned, so I missed out writing the p-value. So I'm going to go back and introduce p right at the beginning. So pv data.p, so that should be equal to 10^6. So, and that's basically my pressure. Unit is in Pascal. So we missed out that at the beginning, so now we've run the model. So we clear the screen again, and then we run it again. I mean, this is what you do as part of your code development. So what is done is now run, and then it's documented the results with all the details so that we want. So the set of parameters from analysis are given, the diameter is given, the radius, everything, then the sigma t's and epsilon and delta t are all calculated automatically for you. So at least you've got an idea of what the results would be. Final thing that you may want to do is, which again Abacus MATLAB gives you, is to try and publish this information. So if I click publish, so how do you want to publish? So this is, if we publish under this section, you could publish this particular thing. Again, it's a good thing to do because it then creates an HTML basis of your code that you can then utilize going forward. So this is what we need to do with the publishing. So this is running in the background, and it's going to display your result in a nice and interesting way. So yeah, so you've got like a documentation about the code created in a web browser form. So you can embed it on your web page, you can share it with students, and it looks really nice the way the code is laid out for you. And then at the base of it, so if I expand this, so at the end of it, it also gives you a typical prediction. So this is what I will do. I'll publish my data and save it, and then use it as a tool for sharing with people. So that's the purpose of this video. If this is the kind of content that you're interested in, do please subscribe to my Getting Started with Modeling YouTube channel, and please do click on the notification button, so when contents like this are created, you'll be the first to see it. So thank you for your interest and watching so far, and I'll see you in the next video. Bye bye.